Hello everyone, welcome to video 7.1 Discrete Energy and Radioactivity, part 1 of 2. Instead of starting on the slide with all of the data booklet references, we're going to be starting quite a bit later on this slide, which is on isotopes. The formulas that are introduced at the beginning of this section are actually not going to be relevant for us in our studies of this section. All right, so isotopes. Well, before we understand what an isotope is, you have to refamiliarize yourself with what an atom is and what it is comprised of. Well, atoms are the basic building blocks of nature. Let me just switch to the page here. An atom contains three primary subatomic particles. Those are the protons, the neutrons, and the electrons. You probably remember that protons have a positive charge, electrons have a negative charge, and neutrons are neutral. They have no charge. Now, specifically, where are these particles located? The protons and the neutrons, these are located in the nucleus. So this is in the center of the atom, whereas the electrons orbit the nucleus. Now, in grade 9 science, you would have learned about something called a Bohr-Rutherford diagram, which essentially meant inside of the middle of that diagram, you would have, for example, the number of protons. So let's say this is helium. Helium is the second element on the periodic table, so it has 2 protons in its nucleus. Now, it has 2 protons and it has 2 neutrons. I'm going to sketch the neutrons as particles with the number 0 inside, and orbiting around, you would have drawn the 2 electrons. Now, something that you would probably remember from your study of grade 9 science is that the first orbit can contain up to 2 electrons. The next one can contain up to 8, and then 8, etc. If you study grade 11 and 12 chemistry, you're going to learn that this model is not 100% accurate, but for our purposes, it's sufficient. So the idea is we've got the nucleons. So this is a special name given for the particles inside the nucleus. We've got the nucleons inside the nucleus and then the electrons orbiting outside. Now, generally speaking, if an atom is neutral, so the entire atom, if it's neutral, then that means there is no net charge. No net charge means it has a charge of 0. So if it has 2 positive charges, it has to balance that with 2 negative charges. So overall, this helium atom, it has an overall charge of 0. If it has more electrons than protons, then it would have an overall negative charge. If it has less electrons than protons, it would have an overall positive charge. Now, with the atom, since you've got the nucleus made up of the protons and neutrons, what you have to remember is that the nucleus is very, very tightly bound. There's a very strong force holding the particles in the nucleus together, which we'll learn about later in this video. It is very hard to break that bond and separate these particles. And so it is a lot easier to remove the electrons, which are just orbiting around the outside. So we can manipulate the atom and turn it into something called an ion by manipulating the amount of electrons. Now, ions are essentially atoms that have either gained or lost electrons. If it gains an electron or electrons, that means it has a net negative charge. And it goes by the fancy name of anion. If it loses electrons or loses an electron, that means it now has a net positive charge, right? Because that means now it has less negative charges than positive charges. And we call that a cation. In this course, we're not really going to be making use of the vocabulary anion and cation, although it's good for you to remember it. In chemistry, you'll be making much more use of these. Now, how do you remember which one is this? The one that's more positive, so if I actually spell this with the lowercase letters, the T in cation looks like a plus, and so that's one way you can remember, and anion is the other one. But what I just want you to know is that an ion either gains or loses electrons. Now, in this section, so let me go back to the slides, we're going to be talking about isotopes. So then what is an isotope? if we can actually manipulate the number of neutrons, so if we have more neutrons or less neutrons in the same type of element, the same type of atom of one type of element, you now have what's called an isotope. So starting off on this slide, proton and neutron, these are nucleons because they're inside the nucleus. Now it says here their charge is 1e. So the charge of a proton is 1e. What does the E stand for? E is sometimes referred to as the elementary charge, and sometimes it's called the electronic charge. So I'm just going to quickly switch screens again. In your data booklet on the table of constants, there is going to be, and if you go all the way down just past the halfway point, there's a lowercase e, and it is referred to as the elementary charge. So there is a value here, and it's measured in capital C, which we saw before is coulombs, the unit of measure for charge. And the value is 1.60 times 10 to the negative 19 coulombs. So this is the charge of what's called an elementary charge. Now, a proton has a positive charge of this value, and an electron has the same magnitude of charge, but just with a negative sign in the front. And of course, neutron is just 0. It has no charge. So going back here, the fact that it says 1e or just plus 1, it's just easier to say that the charge is 1e instead of saying the charge of a proton is 1.60 times 10 to the negative 19 coulombs. Right? We just understand that E, that's the increment of measure or the unit of measure for the electronic charge. All right. All right, so we've got the protons, which will be represented with the red circles, neutrons with the green circles. They have a charge of 0e or just 0. And these are, like I said, these are referred to as the nucleons. Now, hydrogen is an interesting element. Every other element on the periodic table has protons and neutrons inside of its nucleus. Now, hydrogen is the first element on the periodic table and is actually the most abundant element in our universe as a result, helium coming next. But hydrogen actually doesn't have any neutrons in its nucleus. It has one proton in its nucleus, it has to have that, and it has one electron orbiting around. But there are other forms of hydrogen that do have one or more neutrons in the nucleus. So hydrogen itself, it's just the one proton. So right now we're just looking at the nucleus, so that's why you're not going to see an electron in the picture. Just the nucleus of hydrogen, one proton. Another version of hydrogen is called deuterium. Now the prefix "du" means two. All right, so that means there's two nucleons in the nucleus as opposed to one nucleon in the case of hydrogen. Right, so but notice there's one proton and one neutron. Another case would be tritium. Okay, the prefix is tri, which means three nucleons inside the nucleus. Now, I can't have two protons and one neutron. It has to be one proton and two neutrons, because the very fact that it is a type of hydrogen is because there is one proton. The number of protons specifically identifies the element. If I was to have two protons in the nucleus, this would automatically become helium. It no longer would be a type of hydrogen. Now, the fact that you have the same number of protons in each case, but a different number of neutrons, we call these isotopes. Okay, so these are all isotopes of hydrogen. So if you look at a particular one, like deuterium or tritium, these are called species, or they're called nuclides. All right, now the chemistry of an element is determined by the number of electrons surrounding it. And this is also how you determine the charge, as I just explained. Now, the number of electrons that an element has, that's determined by how many protons there are. If you have a neutral atom, you could always gain or lose electrons, in which case you would have a more negative atom or you would have a more positive atom, depending. But if we assume that we always have a neutral atom, that means it always has the same number of electrons as it has protons, then all the isotopes should have the same chemical properties, since all we're doing is changing the number of neutrons. Take water, for example. You're probably familiar with the chemical structure H2O, two hydrogen atoms and one oxygen atom in a single molecule of water. But there is something called heavy water. Now, heavy water is made up of with an isotope of hydrogen, deuterium. So instead of H2O, it's D2O. And so this is actually a denser form of regular water. Now, this is an ingredient very popular to be used in some nuclear reactors, as you learn more about in grade 12 physics. Now, both of those have the same chemical property, but as I just said, heavy water is slightly denser than regular water. All right, now there's 3 numbers that we use to describe an element, right, or a certain type of isotope. The first one is represented with the letter A, and this is the nucleon number. So this is the total number of protons and neutrons inside the nucleus. Okay, so now what is a nucleon? A nucleon is either a proton or a neutron, so that we have one letter to describe each of those as well. So protons are represented with the letter Z, capital Z. Now, that tells you how many protons there are in the nucleus. This is going by another name as well, and that is atomic number. Neutron number is represented by capital N. This is how many neutrons you have in the nucleus. Now you probably see a relationship already forming between these 3 letters. If A is the number of nucleons, and a nucleon is either a proton or a neutron, or rather the sum of the number of protons and neutrons put together, I can say that A is equal to Z plus N. Now in chemistry, you would be looking at the element, and of course, if you study chemistry much deeper, it will get much more complicated than this. But in nuclear physics, we're going to be studying these elements a little bit different. Okay, so let's say we have hydrogen. Okay, so in the top left corner of the letter, which represents the element, so H represents hydrogen, He represents helium, C represents carbon, and most likely you've seen images of the periodic table over and over again. Okay, so the mass number, that goes in the top left corner. The number of protons goes in the bottom left corner, and the number of neutrons goes in the bottom right corner. Okay, so for example, here we have H with 1, 1, and 0. Okay, so this is your standard hydrogen atom. Of course, this number down here always has to be 1 if it's hydrogen. Okay, so this identifies the element. This hydrogen has no neutrons, and so because you have no neutrons and 1 proton, 0 plus 1 is 1. So I have a mass number of 1. Mass number is the total number of protons and neutrons, which also now goes by another name, the number of nucleons. So there's hydrogen. Okay, next up we have deuterium, right? We have 2 nucleons inside the nucleus. We've got H, right? Hydrogen is symbolized by atomic number 1, and we have 1 neutron. And sure enough, as you would expect, tritium is 3, 1, 2. Notice that the bottom 2 numbers always have to add up to the number on the top left. Now, here's the thing. You don't really have to represent all 3 of these numbers, because simply given 1 number, you can figure out, well, actually, given 2 numbers, you can figure out the third, right? Because I know that Z plus N is equal to A. So for sure, we don't need to represent the number of neutrons. So that will disappear. Now notice that all 3 of these also have something else in common, and that's the number 1. Remember I said that refers to the number of protons, and because of that, it refers to its position on the periodic table. Hydrogen is the most abundant element, and it is first on the periodic table, and so that's why the number 1 appears in every single case. You don't need to write that. You can figure out that number simply by looking the element up on a periodic table. So we remove that as well. So all that's left for us is the number on the top left. So again, figure out the number of protons by looking up the element on the periodic table. In our case, the information will be somehow provided to you. You won't have to use a periodic table. And if you do, one will be provided to you. All right, so that is how you're going to figure out the number on the bottom left. How do you figure out the number of neutrons? Take the number on the top left, subtract the number on the bottom left, and you'll get the number on the bottom right. Now, these elements, or these isotopes, they go by other names too. So instead of calling these hydrogen, deuterium, and tritium, isotopes you can also label in a different way. Let me just switch back to the paper for a second. For example, carbon is another element that has many different isotopes. And so 2 examples of isotopes of carbon would be carbon 12 and carbon 14. And there are many others, but let's just look at these 2 for now. Okay, carbon 12 and carbon 14, these are actually used a lot in radioactive dating. All right, so let's take a look. Now, I've written these isotopes in a very special way. I've written the name of the element first, and then I put a dash, and then I put a number. Now, carbon, if you were to look it up on the periodic table, you would see that it actually has proton number 6 or atomic number 6. So these numbers are actually the mass numbers. It's the number of nucleons. And so by writing it like this and understanding that carbon is number 6 on the periodic table, I can figure out how many neutrons each of these isotopes has. For instance, carbon 12, this would have 6 neutrons. If it has 6 protons, then the other 6 have to be neutrons. Carbon 14 would have 8 neutrons, and so on. And so this is the naming structure. Element name, dash, mass number, which is also the number of nucleons. All right, so in this case, hydrogen, this would be considered hydrogen 1 because the number in the top left is a 1. Okay, the number in the top left of deuterium is 2, so this would be hydrogen 2. And sure enough, we have 3 nucleons for tritium, so that's hydrogen 3. So there's different naming schemes. All right, let's try this. Which of the following gives the correct number of electrons, protons, and neutrons in the neutral atom copper? Well, this would be copper 65. Okay, so let's, instead of looking at the possible options, let's just work this out ourselves. Okay, that's the best strategy for any multiple choice. Try to work it out yourself if possible. Okay, so we've got copper and we've got 65 and 29. So remember, the number on the bottom left, this tells me the atomic number. So this is the number of protons. This is Z. The 65, this is A, right? This is the number of nucleons, which is the number of protons and neutrons put together. All right, so now this question is asking us for how many electrons, how many protons, and how many neutrons. Okay, so number of electrons, number of protons, and number of neutrons. Well, protons I already figured out. There's 29. Okay, so if you were to look at your handout, 3 out of the 4 options in the multiple choice question have 29 as the number of protons. So we automatically take out option B. All right, so how do we figure out the number of neutrons? Well, that would be right here. So remember, the number of neutrons is going to be the total number of nucleons minus the number of protons. So that's 65 minus 29, right? So 65 minus 29, what is that? That's got to be 36. All right. All right, so we've got 36 neutrons. Now, how many electrons do we have? Remember, the number of electrons depends on the charge of the atom. And the question tells us that we have a neutral atom of carbon, right? So because it's neutral, that means I have the same amount of positive charges and negative charges. And since protons have a charge of plus 1e and electrons have a charge of negative 1e, you need to have the same amount of both to have a neutral atom. So that means I have 29 electrons. Something else, because this is written, copper 65 is written like this, you can also write the name given the new scheme like this, copper 65. All right, so the answer 29, 29, 36, going back to the slides, the answer would be D. All right, let's try this. Ag102, Ag103, and Ag104 are all isotopes of the element silver. Which one of the following is a true statement about the nuclei of these isotopes? Okay, so A, all have the same mass. B, all have the same number of nucleons. C, all have the same number of neutrons. Or D, all have the same number of protons. So we want to figure out which one of these is true. So let's look at A first. All have the same mass. Well, we're looking at the nucleus, right? So what do we know about the nucleus of these isotopes? Well, I know that this number here, 102, 103, and 104. Oh, and by the way, so instead of just writing silver 104, I can also just put the chemical name and put 104. Actually, let me pop over to the sheet here for a second. So also, in addition to writing copper 65, I can also just write Cu65. Okay, so you can just write the chemical symbol and then put dash and the number of nucleons. Okay, Well, remember that the number on the end here represents the number of nucleons, the number of protons and neutrons in the nucleus. So if you have more particles, and it's not as if one of these particles has zero mass, they all have some mass, even if it's very, very, very small. Actually, and this is where I'm going to switch back to the formula sheet again. If you're really interested to know what those masses are, we're not going to be using them in grade 11 physics. We'll be using them in grade 12 physics. But if you go to your fundamental constants, so past the halfway point, you're going to see m sub e, m sub p, m sub n. And these are the electron, proton, neutron, what's called rest mass, okay, in kilograms and some other units, which we'll get into later on. Okay, but what you're going to notice is if you look at the mass in kilograms, they're extremely small. The proton and neutron have almost the same mass, and they're on the order of 10 to the negative 27 kilograms. All right, so but an electron is even smaller than that. It's almost 1,000 times smaller in mass, and it's on the order of 10 to the minus 31 kilograms. Okay, so regardless, the idea is even though it's so small, there is mass. So if, for example, Ag102, Ag103, Ag103 has one more nucleon than Ag102, so it's a little bit more massive. And Ag104 has two more nucleons than Ag102 and one more than Ag103. So it also is more massive than each of those. All right, so A is incorrect. B, all have the same number of nucleons. Well, each of these numbers is different, and that is the number of nucleons, so that is also incorrect. C, all have the same number of neutrons. Well, the very fact that they're isotopes, by definition, means that they have different numbers of neutrons. And we can clearly see that because their number of nucleons is different. So C is also incorrect. D, all have the same number of protons. That is the only answer here that is correct. Remember that the number of protons is what uniquely identifies the element. And since all of these are silver, Ag, that means they all have the same number of protons. So the answer is D. Okay. Let's talk about fundamental forces for a moment. At the start of this lesson, we looked at the nucleus, and we talked about how it's really hard to extract a neutron or a proton, specifically a proton from the nucleus. We are not the ones creating isotopes, by the way. If you're wondering, well, how do you then add and subtract neutrons from the nucleus? Well, generally speaking, we're adding the neutrons, and it's not that, well, we are not adding it ourselves. This is just a simple byproduct of what's called radioactive decay, which we will see in the coming up slides. So let me just pop over here for a second and look at this picture I drew in the beginning. One of the first things you learned in grade 9 science was something called the law of electric charges. And what that law told us is that like charges repel and opposite charges attract. Now, if you really thought about that closely, you would have realized that based on that explanation, there is no reason for the nucleus of an atom to actually stay together. Atoms shouldn't exist, and therefore matter shouldn't exist. After all, in the nucleus, we have two positive charges for a helium atom, or if you have an even heavier atom like silver or gold or platinum, it's going to have even more protons in the nucleus, more like charges to be repelled by, so a huge repulsive force. Now, some argue, well, we'll say that, well, it stays intact because you've got the electrons and the protons are attracted to the electrons. But even that argument doesn't make sense because if the protons are attracted to the electrons, they will have an even bigger reason to move away from the nucleus. So being repelled from themselves and being attracted to move outer and move further away from the nucleus. So then the question becomes, how do they stay so close together? Well, think of it like this. If there is one huge force pushing them apart and they're still together, that means there's an even bigger force keeping them together, right? So let's go back to the slides. So first things first, so you get used to some new vocabulary, that huge repulsive force, or even if it's attractive or repulsive, if it's with electric charges, we call it the Coulomb force, right? And remember that charges are measured with units of coulombs, so that's where that word comes from. But the fact that the nucleus does not blow apart and atoms and matter do exist means that the stronger force existing there has to go by some other name, and we call this the strong force. This is also known as the strong interaction or the strong nuclear force, or sometimes just the strong force. Now, the strong force, while it is very, very strong, much stronger than the electromagnetic force. It works over very, very short distances only. And so when you hear the expression opposites attract, it's true, but in fact, likes attract much, much, much stronger, but only over very short distances. So there's a new twist on an old tale. Okay, practice. The nucleus of an atom contains protons. The protons are prevented from flying apart by A, the presence of orbiting electrons, B, the presence of gravitational forces, C, the presence of strong attractive nuclear forces, or D, the absence of Coulomb repulsive forces at nuclear distances. Well, right away, let's just look at D for a second here. The absence of Coulomb repulsive forces at nuclear distances. That repulsive force, and this is actually something interesting about this electromagnetic force, which is electric repulsion and attraction, that force can work at any distance. As long as that distance is bigger than 0 and is less than infinity, and that concept that shouldn't actually exist. So from anything bigger than 0, that force will exist, however small, however big. Right, so D is not correct. C, the presence of the strong attractive nuclear forces. That is absolutely true. It is the presence of this force that keeps the nucleus together. B, the presence of gravitational forces. While they are attracted to each other through the gravitational attraction because they have mass, it's an extremely weak force. So not only is gravity a weak force, but their masses are very low, which is going to be an even smaller force. Part A, the presence of orbiting electrons, like I said, that would actually pull the nucleus apart faster. Okay, so the answer is C. All right, so let's look at these 4 forces. In fact, in the beginning of the course, we looked at all sorts of different types of forces. There is a tension force, there's an elastic force, there's a friction force, a normal force, a gravitational force. Right? There's all sorts of forces. But at the end of the day, they can all be categorized into 4 main groups of forces. Okay? And those 4 main groups of forces are the strong force, the electromagnetic force, the weak force, and gravitational force. Okay? So believe it or not, a lot of those forces that we're studying, whether it's electric or tension or normal force or friction, a lot of those forces fall under the umbrella of electromagnetic force. Okay, so we won't get into that too much, but if you are interested in learning more about that, please feel free to reach out to me. All right, so strong nuclear force, as you can see in the diagram, it happens between nucleons, so protons or neutrons inside the nucleus, and it holds them together. So it's an attractive force, extremely strong, but only across very, very short distances. That short distance is usually around the diameter of an atom. Okay. Electromagnetic force. Now, electromagnetic usually is used to refer to radiation, okay, which is light, either visible light or ultraviolet or microwave, infrared, X-ray, gamma. There's so many types of radiation. Okay, but electromagnetic falls under the guise of light, heat, and charge. The weak force. Now, this is also sometimes called the weak nuclear force. Okay, so you might recognize this WMIS symbol. It's a hazardous symbol, which means a radioactive substance. Okay, so radioactivity, which we will be looking at after this topic. We're going to be studying that in the weak force. Gravitational force you're familiar with. This is what causes objects with mass to be attracted to each other. Okay, so for example, the apple being attracted to the earth and falling to the ground. In order from strongest to weakest, you are looking from left to right in this diagram. And when we say strongest to weakest, it is really actually a huge scale. The strong nuclear force is just absolutely magnificent. Sometimes these 2 middle forces, the electromagnetic and the weak force, are combined into what's called the electroweak force. Here are the ranges. So like I said, the nuclear force works over very short ranges, usually across the diameter of an atom. The electromagnetic force, it has an infinite range. The weak force, which is responsible for radioactivity, also operates over a short range. And gravity, like electromagnetic, has an infinite range. So believe it or not, you are actually attracted to that supermassive black hole at the center of the Milky Way galaxy called Sagittarius A*, right now. And it's attracted to you too. It doesn't matter how far you are away from something, you will be gravitationally attracted to it. However, gravity is not only the weakest force, the magnitude of that force drops substantially the further you get away from that object. Don't worry about the last piece on this slide, which tells us about the force carriers. If you're interested, you can look into it, but this is something that gets covered at the end of grade 12 physics. Okay, finally, we move on to radioactive decay. There are certain particles that are considered radioactive, which means that they release gamma rays, they release particles, they release these particles which are highly energized and can cause destructive damage to human tissue. Now, in 1893, there was a very famous couple, Polish and French scientists Pierre and Marie Curie. They announced the discovery of two radioactive elements, radium and polonium. Now, when they placed these elements near a radio receiver, that radio receiver began to act very strange and it started to make all sorts of different noises. Okay, now, there are other ways to demonstrate evidence for radioactivity coming from certain elements. Now, radioactivity means, like I said, that you have certain elements that release special particles that give off radiation, that have certain amounts of energy. Now, that energy can be dangerous. Now, in some cases, it might not be. So, for example, in 1896, there was another scientist studying this at the same time in France. His name was Henri Becquerel. He discovered that, now Kodak, I'm sure you've heard of. Kodak used to make film and they might still make it, although this is a very old company. So back in the late 1800s, they would actually produce film for the cameras back then. Now, that film was placed inside of a box that was completely sealed off, and yet this box was placed next to one of the elements he was working with that, unbeknownst to him at the time, was giving off this radiation. And that radiation passed through the box and caused the film to become darker. And this is what first led him to the idea that, well, this element must be giving off some kind of radiation. Okay, and it was radioactive. All right, now studies show that there are three types of radioactive particles. The reason the second bullet is crossed out here is because we'll study this in grade 12 physics. And the animation that you see on this slide, you don't need to worry about it. This is also something we're going to study in grade 12 physics. So this topic will come up again, but we will study it much more extensively there. So don't worry about this diagram and the numbers here. The three types of particles are alpha particles, there is a beta particles, and we have gamma rays. Now, gamma rays, if you interpret light to be a particle, we would call that particle a photon. Okay, well, let's start with alpha particles. So I'm sure you're familiar with the symbol alpha at this point. An alpha particle really just is a helium nucleus, and specifically we call it a helium-4 nucleus because that means there would be 4 nucleons, 2 protons and 2 neutrons. Beta particles, represented by the Greek letter beta, these are electrons that come from the nucleus. And gamma rays, these are photons, and photons, which are particles of light, they have no mass and they have no charge. Now, if a nucleus emits an alpha particle, let me just do that one more time. Let me go back. Notice that this atom is originally americium-241. Okay, so depending on the atomic number and number of protons of americium, you would subtract that from 241, the number of nucleons, and obtain the number of neutrons. Now, when americium-241 spontaneously decays, it decays into, oh, hang on one second. It decays into neptunium-237, and at the same time emits what's called an alpha particle. So there's the alpha particle. You've got 2 protons and you've got 2 neutrons. Okay? Remember, the alpha particle is a helium-4 nucleus. So no electrons. We're not considering electrons here. This is all in the study of the nucleus of these atoms. So just the protons and the neutrons. Now, the fact that americium-241 lost an alpha particle, so it lost 4 nucleons, that's why the number 241 went down by 4. It went down to 237. How did we know that it went from americium to neptunium? Well, if you had a copy of the periodic table in front of you, you would see that neptunium is 2 spaces to the left or 2 spaces down from americium. you lose 2 protons. So however many protons americium has, subtract 2 from that, and you have neptunium. Now, alpha particles on average all have about the same amount of energy, 5 mega electron volts. Now, you've never seen this unit before, so let me talk about it for a little bit. Now, the prefix mega, you know, so we don't stress about that part. So this is about the average energy of the alpha particle, give or take, you know, a little bit. So again, we know what this prefix means. It means mega, it means times a million or times 10 to the 6. But this you've never seen before, and you're going to be seeing it quite a bit when we study particles this year and when we study grade 12 physics. All right, so this is what's called the electron volt. Now, by definition, the electron volt is the amount of work required to move an electron across a potential difference of 1 volt. All right, now the whole point of having this new unit, so if you're wondering why don't they just measure the energy in joules like every other unit of energy? Well, because these are very, very small amounts of energy. So instead of having some extremely tiny number times 10 to the minus 26 or 10 to the minus 19 joules every single time, it just became easier to express things in terms of a new unit called the electron volt. Now, a formula that, let me just go to the formula sheet here. We never actually studied section 5.1 because I mentioned that we would be studying this in grade 12 physics. But what I did mention is that there was one formula here that you could use to try to remember a formula that you were introduced to in a different section, and that's right here. V is equal to W over Q. Okay, so if I use that formula, V is equal to W over Q, you can see that the potential difference is the work per unit charge. So if we want to know the amount of work based on this definition, work is equal to Q times V. Okay, so by definition, the electron volt is the amount of work required to move an electron across a potential difference of 1 volt. Now, from what I said earlier in the video on the formula sheet, the charge of an electron is E. Now, specifically, it's negative E because it's an electron, but let's just go with the magnitude for now. Okay, so V, this is the potential difference. If it's 1 volt, right, so we can just say 1 V. Okay, so that means the work is equal to E times 1 V, if that makes sense. Okay, so, well, what is work? Work is the amount of energy or the change in energy that gets applied to a certain situation. So the change in energy is given by E times V, which is the electron volt. If this derivation is a little bit confusing to you, don't stress about it too much. What I want you to remember is this. E, so again, let's just pop over to our formula sheet. E on our table of constants is 1.60 times 10 to the negative 19 coulombs. And the voltage is 1 volt. Okay, so this gives us 1.60. Now, there is a derivation for this, but when you multiply volts by coulombs, you're actually ending up with joules. Okay, so this is 1.60 times 10 to the negative 19 joules. So what that's showing me is that 1 electron volt is 1.60 times 10 to the negative 19 joules. So either you remember the derivation, which is important, or I should say, you have to remember this. 1 electron volt is 1.60 times 10 to the negative 19 joules. All right, so if I have 5 mega electron volts, which is the average energy of an alpha particle, that means I multiply this side by 5, that would be 5 electron volts. Multiply this side by 5, you have a certain number of joules, and then multiply each side by 1 million to figure out how many joules you would have. So let's just quickly do that. Okay, so if you have 5 mega electron volts. That means you have 5 times 10 to the 6 electron volts. Remember, anytime you want to change your units in physics, you multiply by 1, but you have to pick your 1 very carefully. So this is going to be 5 times 10 to the 6 electron volts. Always replace your 1 with an empty fraction. The unit that you're trying to remove, electron volts, if it's in the numerator, you stick it in the denominator, and the unit that you're trying to extract, you put that in the numerator. Okay, so now I'm trying to figure out what ratio of what to what is equal to each other. So this ratio has to give me an overall value of 1. Based on this statement right here, I know that 1 electron volt is 1.60 times 10 to the negative 19 joules. And so what I would do is I would say 5 times 10 to the 6 times 1.6 times 10 to the negative 19. So 8 times 10 to the negative 13 joules. And so just looking at this, you can see why it's more convenient to state the amount of energy like this compared to this. Right? If I tell you that one particle has an energy of 5 mega electron volts and another has an energy of 1 mega electron volt, well, it's a lot easier to make that comparison and say that, well, this one is 5 times more energetic, compared to comparing numbers in scientific notation that don't look very pleasant like this. All right, let's go back to the slides. So now that you know what an electron volt is, here is the nuclear decay equation. Americium-241 becomes Neptunium-237 plus helium-4. Now, the energy needed to knock electrons off of atoms is about 10 electron volts. And since each alpha particle is having an energy of about 5 mega electron volts, you can see why one alpha particle can easily ionize a lot of atoms. Now, when it comes to radiation, not all types of radiation are harmful. What is very harmful is when the radiation is what's called ionizing. Ionizing radiation is when it has the energy and the capability to destroy cells at the molecular level. Now, we have to look at this from the point of view of conservation of energy. So starting off with Americium-241 and ending up with Neptunium-237 and helium-4, there is some energy stored away in the form of mass. I'm sure many of you are familiar with the equation, probably the most famous equation in all of physics, E is equal to mc squared. Okay, E is energy, m is mass, and c is the speed of light, which gets squared. So what this equation tells us is that energy and mass are really one and the same thing. They are two facets of the same thing. Now, according to this equation, each portion of this equation has energy because of mass. Now, the right side is a little bit short on mass by about 5 mega electron volts. And so that extra energy or that extra mass becomes the form of kinetic energy for the alpha particle. So the alpha particle can actually fly away. Now, that is a little bit dangerous because the alpha particle is radioactive. So if it's moving away, it can then go ahead and damage living tissue that might be nearby. Believe it or not, the smoke detectors in your house, they work by releasing a stream of alpha particles. And yes, those are radioactive. So you have alpha particles entering your house right now, every second of the day, if your smoke alarm is working. Now, why does that not pose a threat to you? Because that alpha particle only survives for a couple of centimeters. So after traveling a couple centimeters in the air, it's gone. Okay, so it's no longer a threat to you. Now on this slide, you're going to see something called mass defect. Okay, the fact that the right side has 5 mega electron volts more energy means that it has what's called a mass defect of 5 mega electron volts. So that the fact that it has less mass on the right, that difference in mass is compensated by having more energy. So the mass and energy on the right is equal to the mass and energy on the left. All right, so that was alpha decay. Let's look at beta decay. Now, even though we had 3 types of decay, alpha, beta, and gamma, beta is actually an umbrella which under it has 2 other types of decay, beta positive decay and beta negative decay. So you have to make sure you're familiar with each type of these decays and how the decay formulas look. Now, in beta minus decay, a neutron will spontaneously become a proton, and then an electron becomes emitted from the nucleus. This usually happens when there are too many neutrons compared to protons inside the nucleus. So take carbon-14, for example. So remember, carbon, I said, has atomic number 6. There are always going to be 6 protons when you have carbon. If you have less or more protons, it's no longer going to be carbon, but whatever other element is represented by the number of protons. Now, because this is carbon-14, the 14 tells me that I have 14 nucleons, or protons and neutrons, in the nucleus. Since I know 6 of those are protons, 14 minus 6 of them are neutrons, or 8 of them are neutrons. Notice there are more neutrons than protons. So one of these neutrons will spontaneously decay. Okay, so one neutron will become a proton and an electron. Now, if you lose a neutron, that means you go from 8 neutrons to 7 neutrons. And since one of those, well, since the neutron decayed into a proton and an electron, one of those protons is obviously going to be in the nucleus now because the neutron was already in the nucleus. So now instead of 6 protons, I have 7 protons. The electron is going to be given off as a byproduct because this came out of the nucleus. So this is leaving the system. Now, something to notice is that instead of 6 protons, which would have been carbon, we now have 7 protons. So this is an entirely new element now. So carbon-14, when it undergoes beta minus decay, it decays into nitrogen-14. It still has the mass number 14 because now instead of 6 and 8, you have 7 and 7. Right? So that number stayed the same. Now, in addition to having an electron being emitted, there's another particle which is called an anti-neutrino, which also gets emitted. You don't need to worry too much about what the anti-neutrino is, other than the fact that it has to be there to conserve energy. So the total amount of mass and energy on the left side of this nuclear reaction equation has to equal the total amount of mass and energy on the right side. And it just so happens if you take the mass and energy of nitrogen-14 plus this extra electron, it's still a little bit short. There's still a mass defect compared to carbon-14. And so the anti-neutrino is there to compensate. And it's given the additional kinetic energy. Excuse me. So there's the nuclear decay equation. Carbon-14 decays into nitrogen-14 plus an electron plus an antineutrino. Notice that the antineutrino is given this interesting V symbol. Okay, so it's sort of like a cursive V. Okay, so this symbol here, okay, this is called mu, and this is the symbol for a neutrino. And then when you put a horizontal line on top, this is now for an antineutrino. So you're going to see where the neutrino comes up as well. All right. The symbol for electron, lowercase e with a minus sign. If you don't put the minus sign, it's not going to be considered an electron, and the equation will be wrong. All right. Now let's look at the other type of beta decay, beta plus decay. In beta plus decay, usually you have more protons than neutrons, and so the proton decays and becomes a neutron and what's called a positron. And that positron is emitted from the nucleus. Now, a positron is kind of like the evil twin of an electron. Instead of having a negative charge, it has a positive charge, but has all the same other properties. And in fact, in that way, I guess it's not really the evil twin, perhaps it's the good one. So it has the same mass of an electron, has the same properties of an electron. It even has the same magnitude of charge as an electron, except instead of being negatively charged, it's positively charged. Okay, so these are kind of like two mirror images of each other, just with opposite signs. Now, if you're wondering, well, isn't that what the proton was? Wasn't the proton just the same as an electron with a positive charge? Well, you have to remember that the proton and neutron, those two particles are about 1,000 times more massive than an electron, right? But a positron, it has the exact same mass as an electron. It's what's called the antiparticle pair. Okay, so starting off with carbon-10, right? So 6 and 4 makes 10. We have 6 protons because that defines carbon, therefore 4 neutrons. One of these protons becomes a neutron, and then a positron is emitted from the nucleus. Well, if I have 6 protons and I lose one of them because it decays, that means I'm left with 5 protons, which automatically changes the identity of the element. So instead of carbon, now I have boron, which is number 5 on the periodic table. Now, since the proton that decayed became a neutron and a positron, my number of neutrons is going to go up from 4 to 5. Now, 5 and 5 makes 10, just as 6 and 4 did. So the number of nucleons, or the mass number, is still 10. Now, in this case, I'm emitting the positron from the nucleus, so there it is. And this time, instead of emitting an antineutrino, a neutrino is emitted. We have the nuclear decay equation, carbon 10 becoming boron 10, plus a neutrino plus a positron. Notice that the symbol for the positron looks just like the electron, except instead of a minus sign, you have a plus. And the symbol for the neutrino, as I showed you just before, it doesn't have the bar on top. Another word for positron is an anti-electron, but keep in mind that both of these, whether it's an electron or a positron, these are called beta particles because they're part of beta decay. Okay. Now, in contrast to the alpha particle, it was discovered that beta particles could have a large variety of kinetic energies. So, for example, when carbon-14 spontaneously decays into nitrogen-14 and releases an antineutrino and an electron, they might have the same kinetic energy, a medium kinetic energy, and move off with some speed. Carbon-14 could also decay into nitrogen-14, where the electron that is emitted is very fast and the antineutrino is very slow. There could be any sort of combination here. Whereas if you remember, we said that the alpha particles generally have an energy of about 5 mega electron volts. Now, this is what I was mentioning on the previous slide. In order to conserve energy, there had to be another particle there. And this is where the presence of the neutrino and antineutrino were predicted. All right, the last type of decay, gamma decay. Now, gamma decay is a type of decay where you have an atom that is in an excited state decaying to an atom that is in a more stable state. Things always want to reach their most stable state. They want to reach their equilibrium state. Okay, so here we have plutonium-240. It has atomic number 94. Notice that on the left of this picture there is an asterisk next to its symbol, and on the right there is no asterisk. The asterisk, or this little star symbol, means that this is the higher energy form. And because it's unstable, in order to become stable, it gives off energy in the form of gamma radiation. Now, remember that radiation can have different wavelengths. I mean, it can be very short wavelength, like radio wavelength, or infrared wavelengths, or microwaves. It can be used to the wavelengths that we are used to interpreting and interacting with on a daily basis, visible light, or it can have very high wavelengths, very short wavelengths, which are dangerous wavelengths. Okay, those being ultraviolet, X-ray, and gamma radiation. Gamma radiation is the most dangerous because it has the highest energy, smallest wavelength, and highest frequency. Now, here, when you have gamma decay, you are emitting gamma photons. Okay, so photons with the wavelength of gamma radiation. Now, when this nucleus goes from the excited state to the stable state, or the ground state, it releases a photon. Remember, that's a particle of light. Now, this symbol here, this interesting looking Y shape, so let me just draw that for you. This is the Greek letter gamma. And we use this to represent the gamma rays. All right, let's go back to the slides. So with gamma decay, because it's the same atom, you didn't gain or lose any of the subatomic particles like protons, neutrons, and electrons. All these numbers stay the same, specifically the number of nucleons. You still have 234 on the left, you have 234 on the right, except you have to make sure that the higher energy state has a star next to it. And on the right side, we have the gamma symbol to represent that gamma radiation was emitted. Okay. Now, what can be done with these particles? I mean, what would it take to stop these radioactive particles in their tracks? Well, remember I said you have alpha particles in your smoke detector, and it is the blocking of the stream of these alpha particles which sets off your smoke detector that detects that there is something else in the air. Now, these alpha particles are radioactive, but they're not harmful because, well, they usually die off within a couple of centimeters of air. If you put a piece of paper in front of them, that will also stop them in their tracks. Now, beta particles, right, the positrons and the electrons, these have a charge of -1. They're smaller, they're lighter, they can travel a bit further, up to a few meters. If you put a sheet of aluminum in front of them, they can even travel a few millimeters in the aluminum. The most dangerous of these particles is the photon, the gamma rays, because these are very, very high energy photons. Okay, so this would be the type of radiation that is given off in a nuclear blast. And for something like this, you would need a few centimeters of lead. So this would be the ideal nuclear safety chamber. So having a shelter made up and lined with lead, a few centimeters of it. If you don't have lead and you have concrete, there has to be a few meters of concrete to compensate and act the same as lead. Now, neutrinos are pretty interesting particles. They can move through almost anything, and in fact, they can move through miles of lead. But luckily, the neutrinos are not the particles that we have to worry about. Excuse me. Now, we said earlier that it is not just any type of radiation that is dangerous. It is specifically ionizing radiation, which would be the gamma radiation. Now, why is that dangerous? Because it actually damages the cells. At the cellular level, this is seen as burning the cell. Now, like I said, with the alpha particles, generally speaking, these are dying off within a few centimeters of travel in the air. But if you have gamma radiation, it becomes very dangerous. Okay, so this is the kind of radiation that would be given off in a nuclear attack, or in the unfortunate case of a nuclear power plant issue, as they had in the Ukraine, at Chernobyl site. So they had a massive nuclear disaster. Okay, we will be studying that a little bit, either this year, but for sure we will be studying this a lot in grade 12 physics. Ionizing radiation can have devastating effects on your body, as shown in this picture. This man's skin has been severely damaged. Now, how do you protect yourself from this ionizing radiation? Well, there's a lot of sources that are natural, and there's a lot of sources that are artificial, and it actually varies depending where you are on the Earth. Okay, so for example, if you are at a different altitude, if you're higher, closer to the sun in a sense, you would have more ionizing radiation towards you. And depending on what type of country you are in the world and what type of technology it uses, you might also be exposed to more ionizing radiation. So the table on this slide refers to ionizing radiation from natural sources. Well, we've got irradiation just in the air. So you can see the air in the United States is quite bad. It's rated at 2.28 versus 0.4 in Japan. Japan's air is very, very clean. Now, where does this come from? Mainly from radon. Now, all of these numbers are measured in a unit called millisieverts. This is the unit that we measure radiation dosages in. You can also get radiation from ingesting food and water. You can get radiation from the ground, and you can get radiation from space. Okay, so in total, you can see that the US has more than twice the amount of radiation from natural sources compared to Japan, and about 30% more than in the world. And on this slide, we've got radiation sources that are artificial. Medical radiation sources are huge, right? So if you're going for a CT scan or you're going for an X-ray, try not to go for those unless they're absolutely necessary, because you are exposed to radiation every time. In the USA, 3 millisieverts, Japan 2.3, and in the world overall 0.6. But then you have to remember that the world, it depends on where you are. Perhaps they don't have access to this type of equipment. So there's all sorts of variables you have to consider when you're looking at these numbers, which is nice because we have a country like Japan to compare to the United States. Consumer items, 0.13, things like cigarettes, traveling by plane, building materials. Atmospheric nuclear testing, occupational exposure, depending on where you work. If you're working in a mine, you're working in the medical field, or you're working with aviation-related careers. Overall, we can see that the United States, 3.14 millisieverts, Japan 2.33, and the world 0.61. Again, it's probably better to compare the US to Japan because there are many other variables to consider when comparing it to the world. Okay, the last slides that we're going to look at is this radiation dose chart. These are not exact measurements, but it does give you a general, pretty solid idea of comparing radiation from different sources. Okay, so notice what it says here on the slide. It says 1 sievert all at once will make you sick and too many more will kill you. But we safely absorb small amounts of natural radiation daily. Okay, so the same number of sieverts absorbed in a shorter time will generally cause more damage, but your cumulative long-term dose plays a big role in things like cancer risk. Okay, so let's start with the smallest one, sleeping next to someone, 0.05 microsieverts. Okay, if you live within 50 miles of a nuclear power plant for a year, that's 0.09 microsieverts. So this is actually something I'd like to point out. Eating one banana gives you a little bit more radiation exposure than living within 50 miles of a nuclear power plant for a year. Okay, now if you're looking at that saying, oh my God, I just had a banana this morning or I had one yesterday, it's okay. It's not a lot, but you shouldn't overdo it, just as you shouldn't overdo anything. The reason why bananas are radioactive is because they contain radioactive potassium. Now, even worse than a banana, which I don't believe is actually on this chart, is cigarettes. Cigarettes actually have a lot of radiation inside of them. One big reason why they can also cause cancer. All right, let's look at this. An arm X-ray, 1 microsievert. Using a CRT monitor for a year, 1 microsievert. Airplane flight from New York to Los Angeles, 40 microsieverts. A dental X-ray, something a lot of you probably have done and will continue to do, 5 microsieverts. Chest X-ray, 20 microsieverts. Notice this entire blue source combined is now this tiny little, these 3 little green squares now. Extra dose to Tokyo in weeks following the Fukushima accident, 40 microsieverts. What else do we have here? I mean, there's a lot of stuff we can look at. Let's see here. Dose from spending an hour on the grounds at the Chernobyl plant in 2010. 6 millisieverts in one spot, but varies wildly. Okay, so this is where the nuclear accident was in the former Soviet Union. Maximum yearly dose permitted for US radiation workers, 50 millisieverts. And again, that gets smaller here. Approximate total dose at one station at the northwest edge of the Fukushima exclusion zone, 40 millisieverts. So in Fukushima, Japan, and also in Chernobyl, Ukraine, there's areas that are called exclusion zones, areas that have been frozen in time. So if you were to look at a photograph of, for example, Chernobyl, when the nuclear disaster happened, the entire city was evacuated, and quite a bit of a large diameter from the center of that nuclear disaster was evacuated because it's what's in a region called an exclusion zone. There is such high presence of radioactive particles that people can no longer live there. They had to leave all their belongings behind. School classrooms were left exactly as is. Houses were left exactly as is. Everything is frozen in time, and people cannot go there. They cannot live there for at least another 10,000 years until the radiation finally goes down to a safer level. Okay, so that's what's called an exclusion zone. Fatal dose, even with treatment, 8 sieverts. Okay, but if you have 4 sieverts, it's usually fatal radiation poisoning, survival occasionally possible with prompt treatment. So again, this is all just relative. These are not exact values, but it does give you an idea of radiation exposure. So overall, try to keep yourself safe from these sources. Don't eat too many bananas. And this is the end of 7.1 video part 1 of 2. Stay tuned next time for video part 2 of 2.